So I apologize. Okay, first thing, obviously we're going to be having our exam now on Thursday. I'm going to make an announcement about that, so I'm just going to, I have a new tab in the notes just for the exam 3 review, and I'm going to do that first. So our exam 3 is going to be Thursday, November 12th. But I made a decision about how I'm going to be offering this exam. So you all know that Dead Week begins Thursday and extends through next, I guess, Thursday, right? Because next Thursday is a reading day. So you're not supposed to give exams during Dead Week. So because of that, and this semester stressful, what I'm going to do for exam 3 is let you do it virtually, and you may use your notes for exam 3. Okay? So you don't have to show up here. I'll just email everyone the exam at 8:30, and we'll just proceed that way with exam 3, and you are allowed to use your notes. So I'm just going to mark this on here, and for those of you who are on the video, hope you watched the video today, virtually with notes. Okay? So that's my update on that. We were also sent as faculty instructions to give you guidance about the final exam, just so you could plan accordingly for when you're departing campus and all that. So I also want to announce for the final exam, will be given the same way as exam 3. All right, so it'll be virtual as well. All right, so I'll just throw that in here too, so you have this in writing. So the final exam, it'll still be on Tuesday, November 24th. And it will be virtually with notes. Okay? So our final 2, so this is a big chunk of your grade, right? So this is an opportunity to do really well and improve your grade if it's not, where you want it to be. So each exam, if you look, I'm trying to find, I have 1,000 papers up here, but I believe it's up here. Exams are 15% of your grade, and then that final exam is 20%. So these 2 things that you're going to take virtually count for a little bit more than a third of your total grade for the course. All right, so really, plan on taking advantage of that. Okay, with that being said, let's talk a little bit about the exam. We know exam 3 is only on sections 2.1 through 2.6. So I figured I would just go through like we've done for previous exam reviews and just go through the problem types. All right, so for section 2.1, I'm going to exit full screen here. And as I do this, I'll look at our previous quizzes, because one thing that I've been trying to stress too is when you want to try to figure out what types of problems you're going to see on the exams, the quizzes are a really good resource to try to figure that out. Like if you take your quiz, I think it's quiz 3 and quiz 4, and then look at your exam 2, you're going to see there's, just about every question from those quizzes also appeared on exam 2. So that's kind of the clue as to, what kind of questions are you going to see from sections 2.1 through 2.4 at least, because you had quizzes 5 and 6. So they're going to be a good thing to look at. So as we go through the different types of problems you're going to see, I'll kind of point out the ones that were on the quiz. So for section 2.1, there's graphing coordinates, right? So graphing chords on the Cartesian plane. Okay. And we have been doing that in subsequent sections when we were graphing things like piecewise functions and lines. So that's probably not that big of a deal. But then what we did was, since we were, gained that knowledge, we were able to figure out the distance between 2 coordinates. Right? So we give the distance formula, and I'll every time there's a formula, you're going to see that on the exam. So you get the distance formula. That'll be there, just like it was on quiz 1. And then we also figured out the midpoint between 2 points. or coordinates. When I say points, coordinates, I'm meaning the same thing. And then you'll be given that midpoint formula. So then we applied using that distance formula to determine the types of a type of a triangle that's created from 3 coordinates. So determining triangle types. So this was determining equilateral versus isosceles versus scalene. So equilateral have equal sides, all equal sides. Isosceles, 2 of the sides are equal, and then scalene, the 3 sides are different. So you work through how to do that. And then finally, actually that was it. So that was all of section 2.1. So I guess I could go here and say this is problem type number 1, we got number 2, number 3, and then number 4. And if you go and looked at quiz 1, right, I'll just briefly read the questions. You know, it's find the distance and midpoint between 2 coordinates, identifying this triangle given 3 points. And that was pretty much, you know, everything that you had to do. So all of these things were on quiz 1. You had to do all of them. Okay? So if you're looking for the types of questions, not only would the homework from that section be useful, but going over that quiz 1 would also be useful. Okay. So that's section 2.1. So moving on to 2.2, we have, what did we do? Okay, we were sketching graphs. With tables, right? I gave you x coordinates, and I gave you an equation, and you would figure out the y coordinate by plugging in the x coordinate, and that gave you basically these ordered pairs, right, which represents the points on the graph. You put the points on the graph, and then you go ahead and do it. That was pretty simple. Then we have intercepts. So figuring out the x and y intercepts for a graph given an equation. Then we looked at symmetry. Remember, we had 3 types. We had x-axis symmetry, y-axis, and origin. So know how to do those tests. And I think that was actually it for section 2.2. So when I go back to quiz 5, I keep saying, oh, that shouldn't be quiz 1, that should be quiz 5, my bad. Quiz 5. It's the first quiz after exam 2. We had a question, graph the equation given these x coordinates. You had to graph it. And then number 4 was find x and y intercepts of some equation, and then test the following function for x and y-axis symmetry and origin symmetry. So all of this stuff was also on quiz 5. And again, I'll call this problem type 5, 6, and 7. So quiz 5 is a good review, right? So if you didn't write down the solutions, before you leave today, if you'd like to take a picture of my solutions so you have that when you're reviewing your quiz, please feel free to come up and take a picture of this before you leave. Okay, so I'll leave them out here for you to do that. Okay, so let's look at section 2.3. All right, let's see what we did. Oh, this was the line section. So we'll say determining the slope of a line, right? And that's a formula, right? Slope formula will be given to you. Then we had to, we had to be able to write the equation of a line in slope-intercept form. So write equation of line. And I'll just write it out. It's y equals mx plus b, right? That's slope-intercept. And then obviously being able to graph the line as well. Then we had to write equations of lines. So write equation using the other formula, which is point slope form. Okay. And again, these two formulae will be given to you on the exam. And there were a bunch of different ways to do that. And if you look at quiz 6, you know, all of question 1 was just I give you a point and a slope, write out the equation of the line in slope-intercept form. And then number 2, I gave you a couple different things. So the only other thing in section 2.3 would be parallel lines. And this is the same slope, right? So if I tell you 2 lines have the same slope, determine the slope from the one line and use it in the other. And then perpendicular lines. And this was the relationship -1 over the slope of the first line. So you just take whatever the slope was of your line that you know, do 1 over that value and tack on a negative sign. And that gives you the slope of the other line. And that was it. That was all of section 2.3. And again, all of this stuff was on quiz 6. That was questions 1 and 2 on quiz 6. And then also number 3, which was find x and y intercepts, which you already knew how to do, and then graph the line. So I guess we can call these problem types 8, 9, 10, and 11. All right. So far, so good. Again, feel free to stop me if you're like, wait, I don't remember what you're talking about. But I think this stuff is, we've covered quite a bit of this. All right, a couple more sections to go. Section 2.4. 2.4 was on functions. So this was, let's see what we had to do. So I guess I'll say the first type is determining domain and range. Okay, so again, the domain is a set of all of the values of, we typically use the variable x as the independent variable. Determining the domain is the set of all x values that result in a real solution to the equation, or to the function rather. So when you plug in an x value, you get a real number. If you get imaginary, it's not a part of the domain. If you get undefined, it's not a part of the domain. And then the range is the set of all the real values resulting when you plug into the domain. So we found that 2 different ways by looking at an equation or graph. So I either gave you an equation, you had to figure out the domain and range, or just the domain, and then for graphs, you could figure out the domain and range. And honestly, that's it. I mean, we did that I gave you a bunch of examples, but that's it. That is the only other thing that the real main thing was about, how to just work with functions and finding those things. And again, the last question on quiz 6 was find the domain of each function and then also do it in interval notation. And we've been using that throughout the semester. So again, I'm going to leave the quiz 6 here, so if you'd like to take a picture of it, it'll be here at the end of class. So that's a pretty short section. There wasn't much going on there. All right, section 2.5. This was properties of functions. And we determined, let's see, the first thing we did was actually determining if a function is even or odd, okay? But this was actually the same thing we've done with symmetry back 2 sections ago. So even functions are really y-axis symmetry. And then odd is origin symmetry. So if you're given a function, you just have to do those same procedures, determine if it's even or odd. The next thing was determining intervals of increase and decrease. Given a graph. So if the slope between 2 points was positive, we would say that part of the function is increasing. And then there'd be a place where you change from positive slope to negative slope. We call that a relative maximum. So determining relative maximum. And then if you were decreasing in a function and then it changes to increasing, that would be a relative minimum. And again, you would have to see the graph to be able to do that. The next thing was average rate of change. And again, I'm saying you're getting the formula, but you're going to have your notes too, so you're going to see it in the notes. It'll just be nice because it'll be right on the exam. So if you wanted to figure out the average rate of change, and remember that is kind of like the slope between 2 points, you basically just have to find, if you're given like some f of x, I don't know, 3x minus 2 or something, and I'd have to give you when x changes from a equals some number to b equals another number. So you really just have to figure out what f of 2 is and f of 5 is, and then plug it into this equation to get the average rate of change. Okay. So you'd end up getting a number as your final result for that. And then the last thing was the difference quotient. And that was a formula and also given to you on the exam. So you just have to go ahead, if given a function, figure out what f of x plus h is. So instead of having x into your function, so if I had this same one, f of x equals 3x minus 2, I'd have to find what f of x plus h was and just plug in, instead of having x, I have to plug in whatever's in here, which is x plus h minus 2. I can simplify that and then plug all that stuff back into this equation and then just get what your final result was. Okay? And that was everything from section 2.5. So we have 13, 14, 15, 16, problem type 17, and then we're finally to the last section, 2.6, which was, this was the very short section. This was easy. There was only 2 types of problems. It was writing a linear function if given, as an example, like f of 2 is equal to 4, f of 1 is equal to negative 5, for example, right? So if you're given something that looks like this, you just have to understand what the numbers mean. So the thing you're plugging into the function is the x value, and the result is the y value. So you're essentially giving coordinates. Now, if you wanted to write this function, since you're given 2 points, you can calculate the slope. Then you have to use point slope form to get into y equals mx plus b form, and then just sub out y for f of x. It's that simple. So really, this is the only really new part here, is determining 2 points given that, and then everything else is just a section 2.3, writing out the equation of a line. So that's the first type, and then the last type was graphing piecewise functions. And determining, again, domain and range. Okay. So there we go. So we have a total of 19 problem types as I have it laid out here. Now, we didn't have a quiz on sections 2.5 and 2.6. So my best advice would be just to go back and look at the homework problems that were assigned. Okay, and there were some questions asked about these sections, I believe. Let me just go back to make sure. So at the end of 2.5, yeah, I went over a couple different types of problems for 2.5. Average rate of change and then a difference quotient. And then in 2.6, let's see, I gave you a bunch of examples in class. Yep, and then I went over an example, piecewise function from the homework assignment, and we determined domain and range. Let's see. Yep, I talked about when to submit homework, and I did another one here. Yeah, so I gave you a lot of extra homework problems as examples at the end of 2.6. So again, go back to those, because they're the types you're going to see on the exam. Okay, so before we move on, just want to open up the floor to any questions or concerns you have about exam 3. Does anyone have something they'd like to see one more time? Please, this is the time to do it. And I'm just marking who else came in today. So, anything else? Sorry if I can't see over there. Do you think we're all probably pretty good for exam 3? And again, Liam, yes. Like one of the homework problems here? Sure, absolutely. So we'll go to 2.5. Which one? Yeah, you want me to just pick one? Yeah. Well, I'll pick one that we didn't do yet. So I'm going to put this at the end of section 2. Well, I'll do it right here on exam review. That way you'll know it's here. All right, so I'm going to pick from section 2.5. You want to determine the intervals of increasing, decreasing, and relative max and min? Okay. So let's do, I don't want to do a crazy, well, yeah, let's just go ahead and do it. We'll do 16. So this one's kind of ugly looking, so just give me a second to, but it'll be a good review. So it's got a bunch of points here. So let's just go ahead and go. I'll try to draw this as smoothly as I can. Okay, so I'm just going to give you these points. So -3, -2. This one's -1, 1. This is the origin. 1, 2. And 2, -3. Okay, so let's figure out all the intervals for increasing and decreasing. So let's do increasing first. So increasing is going to be any place in this plot where you have positive slopes. So does everyone see, like, from here, -3, -2 up to -1, 1? Do you all agree that the slope is positive there? And how would you tell? Well, if you picked any point here and then drew a tangent line to it, if that tangent line has a positive slope, then we're increasing. So there's an increasing interval there. How about right here? From the origin up to this 1.2 looks like we're increasing. And then finally from 2, -3, we're going all the way up here to infinity. So it's wherever the slopes are positive is where we have intervals of increasing and decreasing. So if we had to write this in interval notation, for down here, we're starting at x equals -3, right? So we're going to have, we're not going to include -3, right? Because that point down there has a 0 slope, so we're not increasing. So we're going to go from -3 up to -1. We're going to union that with the origin, so 0 to 1. And then we'll union that with 2 all the way to positive infinity. So there's our intervals of increasing. Is everyone okay with that? Right? You just look for the positive slopes. Now for decreasing, it's probably going to be everywhere else unless you have a horizontal line somewhere. So right here, all the slopes are decreasing. Right here, the slopes are decreasing. And then right here. So again, you start all the way on the left and you say, all right, well, We're going from negative infinity all the way to negative 3. We're going to union that with negative 1 to 0, and then union that with 1 to 2. Now, so that's determining intervals of decreasing and increasing. The places where you have relative mins and maxes are where you see the color changes here. So right here is going to be a relative min or max right here, right here, right here, right here. Okay? So relative mins and maxes, I think that's the plural of maxes, we'll see. Okay? They're going to be points. So maxes will be where you're increasing and then changing to decreasing. So where are we doing that in this one? Where are we going basically from the green positive slopes to the red negative slopes? Well, the first one I see is right here at negative 1, 1. That's a relative min, right? Because you're increasing and then changing to decreasing. Same thing at 1, 2. Right? You're going positive in the green here and then red, negative on the other side. So there you go. There's our relative maxes. Now the relative mins are just the opposite. You're starting with negative slopes and then changing to positive slopes. So that's negative 3, negative 2. The origin, 0, 0. And then red to green again would be 2, negative 3. So does that help, William? Does that make sense? All right. Anything else I could go over from any of these sections for exam 3? By the way, the exam is the same length as the other exams, 10 questions, so they're each worth 10 points apiece. So what I'll do is, since you'll submit it to me electronically, and really try to submit it to me as a PDF, because that's how I'll grade it. I'll grade it right on the PDF and then email it back to you, with all the points that are taken off. Yes, Liam? Oh, sure. So I think that's a 2.5 as well, right? So that was 16 I just did, so let's pick another even one. So we want to determine the difference quotient. So let's pick out a nice one here. Yeah, let's just do this one. How about this is going to be number 76. And they're giving us a function, x squared minus x. All right, and we want to find the difference quotient. So I'll put it down here, f of x plus h minus f of x over h. Now before we plug anything in, I always suggest that you do this. We already have what f of x is. That's the second term here in the top. We have that. But what we have to find before we can plug anything else in is, what is f of x plus h? And remember, the thing inside the parentheses is the input to the function. So everywhere you see an x in the original function, we're going to put an x plus h. So what does this look like? Well, instead of x squared, we're going to have x plus h squared minus x plus h. Right? So you'll notice that here we had an x in the original function. We substituted in x plus h, and then we did the same thing with the other x. Now, what we have to do before putting it into the difference quotient is simplify this out. So we're going to FOIL the x plus h and get x squared plus 2xh plus h squared. And then this negative sign here, which a lot of people, I see people making this mistake, is that has to be distributed to the x and the h in this binomial. So it's negative x minus h. All right, nothing cancels out there, but now we're going to be able to plug this thing in for x plus h, f of x plus h in the difference quotient. So let's see what happens. So the numerator here will be x squared plus 2xh plus h squared minus x minus h, and then we're going to subtract the original function. Got to put it in parentheses, x squared minus x, and then that thing's just all over h. Okay, now we got to start, things are going to cancel when you do the difference quotient. So you see that I have an x squared over here, right? And then I'm going to have a minus x squared here. So they're going to cancel. All right. What else goes away? Well, we have a negative x here, but then the negative sign right here and the negative x is going to make that positive. So they're going to cancel. And let's write out what's left. We're going to have 2xh plus h squared minus h all over h. This is typical. You're going to end up with terms that have the h variable. So what happens is you can cancel out the h in the denominator with h's in the numerator. So I could do h and h in this first term, be left with 2x. I can only cancel one of the h's in the second term and get plus h. And then negative h over h is a negative 1. So that's your final answer. So that's the result of the difference quotient. And I think I mentioned to you before, you actually use this in calculus to figure out a function that represents the slope at any location on your graph. But we're not worrying about that in this session. We just want to be able to get to that difference quotient. Okay, anything else from the exam 3 review? Good? Okay, so again, right at 8:30 on Thursday, be looking for an email from me with instructions with the exam. Okay? And then I'll leave these quizzes here if you'd like to take a picture of those before you leave. All right. So that ends the exam 3 review, and so what I want to do is just kind of recap what we've done for the section after exam exam 3. That's going to be part of the final exam. So the next section was section 2.7, so I'll just quickly review that. And I did give you a homework assignment on this. So the first thing we started with in this section was some basic functions, and I gave you 5 of them. Right? F of x equals x, that's just a line, right, that passes through the origin that has a slope of 1. F of x equals x squared, that's a parabola. F of x equals x cubed, we call that a cubic function, it looks like that. And then the square root of x, and then the absolute value of x. And what we were going to do with these functions is transform them. And there were 4 different types of transformation. We had a vertical shift. Okay? So all that means is we have the original function and then we're adding a value to it. So in this example, I started with the parabola, and then I gave you 2 functions, x squared plus 2 and x squared minus 3. So what does that do? Well, that shifts the function and the graph up or down. So if you have a plus 2, that's going to be this orange one here. So instead of being at the origin, you're going to be at 0, 2, because this is our y-intercept. And then if you have a negative number, you shift it down. So vertical shift is pretty simple. Then the horizontal shift would be wherever you have an x term, if there was a plus 2 or a minus something inside a set of parentheses that you're squaring. So instead of just having x squared, you have x plus 2 squared. But what you'll have to remember for horizontal shift is if you have a plus 2 in here, that actually means you're going to shift in the negative direction. So you'll see that in orange here. Instead of being at the origin for this parabola, I shifted left 2. For this one, h of x in red, I had a negative 5, so that means we're going to shift to the positive direction 5, so you'll see that it's shifted from the origin to the right 5 units. So that's horizontal and vertical shifts, and then I showed you how to combine the 2. So I used the square root function. So I said, well, it's the square root of x minus 1, which means we're going to horizontal shift 1 unit to the right. And since it's plus 4, over here we're going to shift vertically 4 units. You see that's what I did. I shifted to the right 1 and up 4, and then simply drew the original square root function at that point. Okay? Then we had reflection. So this is simple. If you have a negative sign in front of your original function, you simply rotate, or think about it, you're going to mirror the function across the x-axis. So I gave you 2 here. I gave you g of x, which was a parabola, and then h of x, which was a square root. And if all we did was make 2 more functions, and we added a negative sign in front of the parabola. You see that the parabola just flipped around the x-axis. And again, if you add a negative sign in front of the square root function, again, it just flips it across the x-axis. So that was reflection. And then the last one was compressing and stretching. All right, so you can think about stretching as widening the function. So I have here in orange, the original parabola function. And now if I added a fraction, or really any fraction between 0 and 1 in front of the original parabola, x squared, what that would do is that is going to widen the function. So that's what you see here in red. All right, this is the g of x widening function. But if I end up putting an integer in front of the original function, so this would be, think about it as shrinking, that's going to be what you see here in blue. All right, so instead of being wider than the orange, it's inside the orange. So that's compression and shrinking. And then there were the four transformations, and if you have all of them in one equation or one function, there's a specific order you have to do them in. So it's HSRV. It's horizontal shift first, stretching, compression, reflection, and then your last thing to do is the vertical shift. So I gave you a nice example here. We, again, are using a parabola. So again, here the original thing was -1/2 times x plus 3 squared minus 4. So I highlighted the four transformations. The first thing we're going to do is the horizontal shift. So you see that here it's plus 3. So that means we're going to move to the left 3. So I moved the normal parabola to the left 3. So that was our horizontal. Then we wanted a stretch. We did that in red. You'll see that we have the 1/2 here. I circled it. So that's going to be widening. So I just drew it wider than the original parabola function. The third thing was reflection, because I have in blue circled here a negative sign. So all I did was I flipped the stretched parabola across the x-axis. And then the last thing was the vertical shift was -4, so we're going to move that 4 units down. And then we have our final solution. Okay? So you'll have to know how to work with each of these four transformations. And then if you have multiple transformations in one function, in what order do you do all of them to get your final graph? And I believe that was it, and I gave you this homework assignment. Okay, so my plan would be I'm going to finish off section 2.8 today and possibly get to section 2.8. I'm going to get to 2.8 and finish that off. So I'll have that 2.8 homework assignment ready to go so that you can submit homework 2.7 and homework 2.8 into a Dropbox next Tuesday. And that'll be for bonus points on exam, or the final exam, okay? So it'll be on 2.7 and 2.8. Unless I can get to 2.9 today, which I'm not sure if I will be, maybe we could add that too, and it'll be even a bigger homework assignment. So I'll explain that at the very end of class. All right, so we got through 2.7. Excellent. Okie dokie. So what we were working on next was section 2.8. Get rid of some of these papers. Here we go. Section 2.8 was on combining functions and then composite functions, which we didn't get to. Now the combining function thing is very simple. We've already really done this stuff before. So I gave you the four basic mathematical operations: sum, difference, product, and quotient. And they're all pretty self-explanatory. Summing means you add two functions together. Difference means you subtract them. Product is obviously you're multiplying them together. And then quotient is one on top of the other in a fraction. So I gave you what that looks like functionally. So on the final exam, if you're going to have questions from here, I'm not going to give it to you in this first column form. You're going to see it in functional form. But that should be pretty obvious. If you have f plus g of x, that just means you're adding them together. F minus g is difference. F times g with a solid dot is product, and then f over g is quotient. So you just have to really know these functional definitions. And then I went through an example. So I don't think you need to see more than one of these because they're all the same. You're given functions, you need to do these basic mathematical operations. So that was where we ended off in this section. Now, the last part of section 2.8, which it's really not too bad in terms of, a little thicker there. All right, so we wanted to talk about the last part of 2.8, which was on composite functions. Okay, so for composite functions, you have to have two functions to start with. So let's say we start with some f of x and g of x. All right, so what does this mean? Well, this is what a composite function is. It's taking one function and plugging it in as the input to a different function. So if I were to write that out for f of x and g of x, and let's just say we're plugging in g of x into f of x, I could write it like this. F of, and then the input to function f would be g of x. Okay? But there's a lot of parentheses there. Okay? And that could get confusing. So we have, we're going to call it a new operation for functions. You may not have seen before, maybe you have. This is equivalent to doing this. F, and then we have an open circle instead of a solid circle, g of x. Okay? So those two things mean the same thing. So if I did the other way, if I plugged in f of x for input to g of x, it would be g composite f of x. All right, so let's just, so this is just pretty simple as well. Let's start off by giving you some functions. I'm going to give you an f of x, call it x squared minus 4. I'm going to give you a g of x, 2x minus 1. I'm going to give you a third function, h of x, and we'll just call that 3x. All right, so I'll give you the functional definition of the composite, and we'll just go ahead and figure out what it is. So the first one, call it number 1. Let's do g composite f of x. Okay. All right, so this is what that means. Is we're starting with the g function. So this is how I would write the next line. G of, and now instead of writing out f of x with all these parentheses, we know we're going to be plugging in f into g because it's the second term here in the composite. So what's f of x? Well, it's x squared minus 4. All right. So everywhere we see x in our g of x function, we're going to plug in an x squared minus 4. So what do we get here? Well, remember, we're starting with this, right, this 2x minus 1. So it's going to be 2 times, now instead of x, we're going to plug in x squared minus 4 minus 1. So we end up getting 2x squared minus 8 minus 1. So our final answer for this composite function is 2x squared minus 9. So that would be the solution of g composite f of x. So that's the functional answer, but you could have something like this. You could say, well, now that we have that, can we figure out the value of that composite when you plug in x equals 1? Well, sure. Now that we have 2x minus 9, instead of having x, we can plug in 1. So that's 2 minus 9, we get negative 7. So negative 7 is the result of g composite f of 1. All right. This is not meant to be difficult. This is just, we need this for the next section. So that's why we're doing it. Okay, number 2. Let's look at the other way. So f composite g of x. All right, so now g becomes the input to f. So we're going to have f of, now we're plugging in g. G is 2x minus 1. So now wherever we see an x in the original f of x function, we're going to go ahead and plug in this 2x minus 1 binomial. Okay, so it's x squared, so it's 2x minus 1 squared minus 4. So you'll see that it looks just like the original f of x function, but instead of x, I have whatever g of x was. And then we just simplify. So, all right, when you do this FOIL, you're going to get 4x squared, let's see, minus 4x minus plus 1 minus 4. So our final answer is going to be 4x squared minus 4x minus 3. So that is the final answer to that composite. So again, we could do something like f composite g of 1 and get, a value for that. So everywhere we see x, we just plug in a 1. So what's that? 4 minus 3, so that's on negative 3. Okay. And we'll just do one more example here to get that h of x function involved. And let's look at h composite g of, and I'll just go ahead and we'll just combine this into one thing. So h composite g of 2. So the first thing to do would be to do this. We know that g is going to be the input, which is x, what is g? 2x minus 1. But we know we're plugging in a 2. Right? So I could do this. So g of x is 2x minus 1, but I'm plugging in a 2 for x. So I can actually just get a number right away as the input to h. So this is going to be h of 4 minus 1, so 3. So now I know I just have to plug in 3 into my h function. So it's going to be 3 times 3. So we get 9. And so you can kind of do it all in one shot if you'd like to. Okay? All right. I mean, that's it. That ends all of section 2.8. So for the homework for 2.8, there's really not much going on. So this is end of section 2.8. I'm looking at page 291, and there's only a couple. We have 25, 27, and let me just quickly go to that. Make sure I'm giving you the right one. Okay, 25, 27. Okay, good. So that'll be doing just the basic mathematical operations, and then 45 through 55 odd, they're going to be doing these composite functions. And then 67 to 73 is again more composite functions, but then also determining that composite function's domain. So again, a little bit more practice on domain, and these are all odd. Okay. All right, so let's see where because we're going to start, we have plenty of time here. We're going to start section 2.9, and then we'll just see how far we can get, and that'll depend on what homework will be due. Not Thursday, because that's our exam. Don't worry about doing the homework for then, but then for the following Tuesday, which is our last class. All right. So we are now on section 2.9. So section 2.9, the topic is inverse functions. I'll make that a little, we'll use the chunkier orange here. Okay, so the first thing we have to understand in order to get the ability to calculate an inverse function or determine if two functions are the inverses of each other, we have to understand something called a one-to-one function. And I'm going to give you the definition. One-to-one. Okay. All right, so if all of the elements in the domain of a function all right, so we're just thinking about all the members of the set of the domain of the function, so all the values in the interval for the domain. If all of those elements in the domain of the function have a unique value in the range of the function is one-to-one. And I'm going to give you a simple example to illustrate this. All right, so let's look at a very basic function that's one-to-one. If I were to give you let's just look at f of x equals x. All right, one of those functions we worked with in section 2.7. We know what that looks like. Okay? I can find, we know what the domain is, right? It's negative infinity to positive infinity, and the range is negative infinity to positive infinity. But if I picked any two x values, so if I picked, let's say, this x value, x1, I know right here, right, I have a corresponding f of x value that's f of x1. And it is what it is. It's some value here, whatever that happens to be. If I picked another one over here, let's say x2, that corresponds to f of x2 over here, okay? And they're different, right? If I plugged in x1 to this, right, I'd have a result that's different from than when I plugged in x2. I'd have a different f of x result. If you can do that for any two members of the, or any two elements of the domain of a function, we would say it's one-to-one. So this is a one-to-one function. Now there is a test for it, but I'm really just trying to get you to understand what this means. So if any two elements in the domain result in two different values in the range, it's one-to-one. So let me show you one that's not one-to-one, and hopefully it'll make more sense. So let's look at something. I'm not even going to give you the actual function, I'll just draw it. So something that looks like that. Okay. Go back to green here. Okay, so I'm going to pick 2 points right here. I'm going to call this x1. All right, so that corresponds to this value here, which is f of x1. But look at this. If I pick right here x2, and that really could be the origin, do you see that it has the same y value? All right, so we call this the horizontal line test. If you do the horizontal line test on a function and you cross 2 points on that function, it's not one-to-one. So whatever the functional equation is for this function, it's not one-to-one. Does that make sense? So if there's two x values that result in the same y value, not one-to-one. And we do have a test for it. and I'll show you that right now. So let's go ahead and show you the test. So this is the one-to-one test. Let's start with the very simple one. F of x equals 3x minus 4. So that's a line, and that's very similar to the example f of x equals x. So this one's going to be one-to-one. But how do you show this algebraically? This is all you do. Okay? You're not going to plug in numbers. You're going to plug in f of x1, set it equal to f of x2, and work through this problem. All right? So let's write the next line out. So the left side of the equation is the original function, but just wherever you see an x, you put a x1. So it's going to be 3x1 minus 4. Do the same thing on the right side, but have x2 in for x. So you get 3x2 minus 4. You work through this and simplify this equation as much as you can. So you can, what happens to the negative 4's? Wouldn't they cancel each other out? Right? If I added 4 to both sides, they'd go away. So I have 3x1 equals 3x2. I'm going to divide this entire equation by 3, and I end up with x1 equals x2. Right? What that means is, if this is your result algebraically, the function is one-to-one. So this is one-to-one. If your result is x1 equals x2, thumbs up, you're good to go. Okay? All right, so we know that one's one-to-one, and then we proved it algebraically. Now, how about this one? We'll call it g of x, and we're going to make it x squared minus 1. Okay? Now, I'm going to graph that over here. All right, this is just a parabola with a vertical shift of negative 1. So we know that we're starting down here at 0, negative 1, and we have a parabola that looks like this. So before we even do it algebraically, do the horizontal line test. What happens? Right, if I do a horizontal line here, you see that I hit two different y values? I'm sorry, I'm hitting the same y value but two different x values. So right away, this is not one-to-one, but we need to be able to show this algebraically. So again, we're going to go through the same process. We're going to plug in g of x1 and set it equal to g x2 and go through this process. All right, so the left side here is going to be x1 squared minus 1. And then the right side is going to be x2 squared minus 1. All right, so x1 squared, you see that the 1's are going to go away, right? They can cancel each other out. x2 squared. And then once you get to this point, you have to solve for one of the variables. So I'm going to solve for x1. So how would I do that? I'm going to take the square root of both sides. So I get x1, but what happens when you take a square root? Right? I'm going to have plus or minus the square root of x2 squared, which is plus or minus x2. So what does that tell me? Well, that tells me x1 could be equal to x2, but x1 is also equal to negative x2. So when your result for x1 has two different values, this is not one-to-one. Okay? Not one-to-one. So you could look at the graph and determine easily with the horizontal line test, but sometimes you might not know how to graph a complex function, but you can easily do the algebraic way. So if your x1 terms end up being equal to more than one value, not one-to-one. Okay? Okay, so why do we care? Well, here we go. We need to know if a function's one-to-one if we want to work with their inverse. So let me just give you some, not terminology, but the the symbology for how you write this out. So if you just see f, right, we know that's a function. If you want to see symbolically what the inverse looks like, we do f to the -1, and it looks like an exponent, all right? We're not actually going to be doing 1 over f, right? That's usually what the -1 exponent is. This is more of a symbolic thing that represents the inverse function of f. If you see f to the -1. So there are some properties that exist for inverse functions. If you did the composite function that looks like this, if you do f composite, so this is why we had to do composites in the previous section, f composite with its inverse of x, the result should be x. And then also, if you did the inverse composite with the original function of x, you should also get x. Okay? So this is how we can determine if two functions are the inverse of each other. So let's do an example. I'm going to give you two functions. I'm going to give you f of x, and these will be simple, 2x plus 3. G of x is x minus 3 over 2. All right? So what we want to do is we want to determine, are these two functions inverses of each other? So really we're trying to figure out is this f -1 and is this g -1? Right? That's our goal. We're trying to figure, is this true? So here's what we're going to do first. We're going to do f composite g of x. Okay? If the result of doing this gives us x, we know g is the inverse of the function f. Okay, so again, this is what we're going to do. We're going to be plugging in g of x, which is x minus 3 over 2, in for the function f. Again, so we're just plugging in the g function as the input to the function f. So let's see what this looks like. Well, we only have one x variable, so it's 2 times this big thing, this big rational expression, and we're plus 3. So all we have to do now is simplify. So you're going to see these 2's cancel out, and we're left with x minus 3 plus 3, and we get x. So again, because we got x at the end of this, we could say g of x is equal to the inverse of f. That is confirmed. Now we can check to see if f is the inverse of g, so then we're just going to do the composite g of f of x. So now we're going to plug in the function f into the input as for g. So we're plugging in 2x plus 3. So that's going to look like 2x plus 3 minus 3 over 2. The 3's cancel in the numerator. We have 2x over 2. The 2's cancel, and we get x. So again, that confirms that f of x is the inverse of g. Okay? Now, I don't believe I'll have enough time to show you the next part. So I think this is, we're close enough. So any questions here on 2.9 as of now? Okay, so this means the homework that's going to be due, I believe it's on the November 17th is our last class. That homework will be the homework that'll give you some points for the final exam, you'll need to submit section 2.7 and section 2.8. Okay? That good? Okie dokie. There we go. Again, if you'd like to take a picture of the homework problems out of the book, please do that. And again, here are the quizzes right here if you'd like to take a picture of those as well. All right, so I won't see you Thursday. It'll be virtual, but I will see you next Tuesday for our final class. Hey, you too.
Thank you.
You're welcome.
Thank you.
You got it. So Bridget, if you, I don't know what you want to do for Thursday, but like you could take it in your dorm room or whatever.
Yeah, I'll just do that.
And so if you would, could you let Mary Ellen pick around though because she's doing Thursday exam?
Yeah.
So just let her know. Do you want 2.8 as well
Yeah.
while you're here? Yeah, so just let her know so she's not looking for you in the morning.
Yeah. So she usually emails, so I'll just
Yeah, and just let her know. That way everyone's on the same page.
Yeah.
All right?
Yeah.
You're welcome.
Thank you.
Hey, you're welcome.
Have a good one.